Okay, we're moving on here to problem number 13. And I notice it says part A. That's really kind of strange because there is no part B. So no, you weren't missing anything. There really is no part B. Okay, let's look at this one. Oh, we get another car one. A car is traveling at 26 meters per second when the driver suddenly applies the brakes, causing the car to slow down with constant acceleration. This is very similar to the previous problem, but a little bit different. Comes to a stop at 120 meters. How fast was the car moving when it was 60 meters past the point where the brakes were applied? So this is similar, but just slightly different. Sorry, I gotta stop and put on my glasses. Okay. First thing we need to do, as usual, is to sketch it. So again, we have our car. Okay, I'll try to make it look a little more car-ish. Okay, that's a little more car-ish. Okay, it's driving, starts with an initial velocity of 26 meters per second, ends up over here at 0. Acceleration we don't know, but we know it's constant, and we know that this distance is 120 meters. But we're also interested in what happens at 60 meters. And we want to know the velocity at this point. Okay, so it's same as last time. We'll go ahead and draw our velocity time curve. We're starting at a velocity up here of 26. And ultimately, for this one down here, let's ignore this for now. We're finishing down here at a velocity of 0. At some time, we don't know what it is, but this is our behavior. It says it was a constant acceleration. So basically, when we're looking at 60 meters, it means we're just going to be at some point here. We don't know what the velocity is, and we don't know the time, but at some point here, when it was decelerating, it got down to some velocity at some time, and then it continued to decelerate. So if we can find the acceleration of this line, then we can find this point on the line. Do we know enough information to find the slope of the line? Sure, we can just go with the two cases we do know, from 26 all the way down to 0. Go to our definition of acceleration. It's a change in velocity over the change in time. Our velocity is going from 26 to 0, so basically 26 meters per second. Over time, do we know time? Uh-oh, we don't know time. So we can't use that formula. Let's come back to our chart here. Constant acceleration. This is the one I was trying, but we don't know time, so that one's not really useful to us right now. This is the one we want. It's relating velocity, acceleration, and distance. Distance is the one we want, so let's go with that equation. V final squared equals V initial squared plus 2A delta x. Okay, V final is going to be 0, just like it was in the last problem, because we end up in a 0 velocity. So rearranging like we did last time, then I'm going to end up with acceleration is negative vi squared over 2 delta x. This is the same as last time, except for our velocity is different. So it's 26 squared divided by 2 delta x, 120 meters. Remember, I'm doing the whole distance here because I'm looking for the acceleration. So it's so far the same as last time. Divided by 2, divided by 120, and I got 2.82 negative meters per second. That looks like I need to put that negative there. Okay, so now I know the acceleration of this line, or the curve slope of this line. So now that I know the acceleration, the slope of that line, I should be able to find this point, right? Because I want to know 60 meters. So can I go straight to the information I need now? Well, not really, because again, I would need time in order to do that. But I can use this equation again. So why don't I just go straight to that equation again? VF squared equals VI squared plus 2A delta X. All right. V final. What is my V final going to be? I don't know. In fact, that's what I want to find, right? So I leave that. V initial is not 0 at this point. It's actually starting at 26. So this is a case where we don't have this one going to 0. So we have 26 meters per second squared plus 2. Acceleration comes down and goes in here. Don't forget the negative sign. Oops, almost off the screen. 2.82 meters per second. Delta x, this time it's 60 meters because we're looking for this point, not all the way to the stopping point. All right, let's multiply it out, see what we get. Don't forget to square it here. 26 squared plus 2 times, ooh, almost forgot my negative, 2.82 negative. I didn't type that in right. Let me start over again. 26x squared. Let's just do minus 2 times 2.82 times 60. And I get, oh, but I also need to remember that's squared on this side. So if I want to find the actual velocity, I need to take the square root of this whole mess there, right? So I got 337.6, but I got to take the square root of that now. I love this calculator. That was sarcasm. Okay, let's try again. Square root of 26x squared minus 2 times 2.82 2 times 60 parentheses equals, and I get 18.37 yada 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 meters per second. So coming back up to my answer, obviously I'm looking for 18.4, and that is the correct answer. Phew, glad it was, because I would have hated to get the wrong answer on film.